So I have the matrix A, so 4, 3, 2, 1, 2, 3, 2, 3, 2, and I want to do a QR decomposition of it using the given sortation. So as usual, I will find my cosine and my sine. Okay, here they are abbreviated as C and S. Okay, but they stand for cosine and sine. Okay, I hope this is clear. And so remember, our cosine is defined as the top element of the column vector over the hypotenuse, and the sine is defined as the element you want to kill over the hypotenuse. And remember that the hypotenuse is simply the square root of the hypotenuse. It's simply the square root of the top squared and the element you want to kill squared. Okay, kill, I mean put to 0, but we can call it kill. And so remember, that's how you calculate your cosine and your sine. And then remember how you place them inside your matrix. That is, the C is in the I position, where I is the row of the element you want to kill, and the other C is in the JJ position, where J is the column where lies the element you want to kill. Our negative sign is in the place of the element you want to kill, that is in the place IJ, and our other sign is in the place JI. So the first of this letter here is the row, of course, and the second one is the column. Okay, it's not clear. Yes. So I will first want to kill this element here, this 3. So j is equal to 1 because we are in the first column, and I is equal to 2 because this is the second row. Okay. And so my cosine is the top element over the hypotenuse. My top element of this column vector is 4. And the hypotenuse, as I said, this top element squared, so 4 squared, the square root of this top element squared, plus the element you want to kill squared, so this 3 squared. Okay, so cosine is 4 over the square root of 4 squared plus 3 squared. And our sine is the element you want to kill, so 3 over the square root of this this element squared, so 3 squared, and the top element squared, so 4 squared. So the hypotenuse again. And so we place them in our matrix here. So as I said, our first cosine is in the ith row, ith column, okay, Cii. Our second cosine is in the jth row, jth column, so here. So right in the middle. Our negative sign is in the ith row, jth column, so actually in the place of the element you want to kill. And our positive sign is in the jth row, ith column, so here. And yes, so this is our first Gibbons rotation matrix. And now if we apply it to A, we get a 0 here as expected. Here we have 5, 2, 2, 1, 3, 3.4, 1.2, and 2. And so that is our first rotation, the result of our first rotation, and we get as a result a sub 1. Let's call it a sub 1. So now again we will repeat this time with this number here. So cosine is the top element, 5 over the square root of this top element squared, so 5 squared, plus the element you want to kill squared, so 2 squared. Our sine is the element you want to kill, so 2 over the square root of the top element squared, 5, so 5, and plus the element you want to kill squared, so 2 squared. So again, this is simply the hypotenuse, which was defined as the square root of the top element squared plus the element you want to kill squared. And our j is 1, okay, first column, and our I is 3, okay, third row. So we again plug in everything here, and don't forget to put 1s in the diagonal and 0 elsewhere for everything else. Also here, you put your cosine and your sines and your negative sign, and then you fill in the remaining diagonal with 1s and 0 elsewhere, okay? Of course, if there's already a cosine in the diagonal, or suppose it a sine, you won't replace it with the 1, okay? Only if there is no cosine and sine in the diagonal, you put the 1 and 0 elsewhere. Yes, so you apply your second Gibbons rotation inside to your first result here, and you get 5.39 So 5.39, 0, 0, 2.97, 1, 2.04, 3.9, 1.2, and 0.59. So again, we have two zeros here now. Okay, this was first result here, and this is now due to the second rotation. So now we will only consider the submatrix here. So 1, 2.04, 1.2, and 0.59. And so that these are submatrix. Let's call it A sub 1, comma 2 by 2, because this is a 2 by 2 submatrix. Sorry, this should be called A sub 2, not A sub 1. Okay, this second result, let's call it A sub 2. So we have A sub 2, and this is a 2 by 2 submatrix. Okay, here. So again, we will repeat, but this time inside the submatrix, very important. So the top element here is 1. We want to kill this element, of course. So the top element of this vector is 1. And so our cosine is 1 over the square root of this top element squared plus the element you want to kill squared, so 2.04 squared. And our sine is the element you want to kill, so 2.04 over the square root of the top element squared, so 1 squared plus the element you want to kill squared, so 2.04 squared. Okay, and so again, now we have two ways to build up our third Gibbons rotation matrix. Either we for the J and the I, either we consider the submatrix, and so in this case J would be 1 and I would be 2. Okay, first column, second row. Do it like that. So J would be 1, A would be 2, and then we build our Gibbons rotations inside the submatrix, and then we do like with the Householder transformation, that is, we fill in the remaining elements with 1s in the diagonal and 0 elsewhere, so that the dimensions match again with the original dimensions of A. Okay, here A is a 3 by 3 matrix originally, so we need to have a 3 by 3 matrix as a Gibbons rotation. So if we only consider the submatrix, we have a 2 by 2 matrix, and so we need to fill in the word. Okay, so 1 here and 0 here. Yes, okay. And yeah, so how do you put this why do you put your Gibbons rotation here, not somewhere like here? Well, simply because your submatrix, your A sub 2 2 by 2 submatrix is here, so you put it in the same place. Okay, your submatrix that we consider is here, and so we put it in the same place for the matrix. Okay, if it would be like here, then you would put it like here. Okay, it's just you put it in the same place as where the submatrix lies that you consider. Or if you don't want to do it like that, you can also simply say that you consider the element of the submatrix, but inside the original matrix. So like here, it was in this place originally, like in this place. Okay, and in this case, if you consider it like that, J would be 2 because this is the second column, and I would be 3 because this is the third row. And so if you do it like that, you can simply do as in the first part, that is you have your J, your I, you put in your cosine, your cosines, your sine, and your negative sign. You put 1s in the diagonal and 0 elsewhere, and yeah, you have your matrix. That's exactly the same thing. That is a shortcut for the Gibbons rotations if you want it. So both ways are correct. If you want to do it like with the Householder transformations, then you can do it. Otherwise, you can do it like that. You consider the element of this submatrix that you want to kill, but inside the original matrix, so at the place inside the original matrix, and then you find your J and your I accordingly. I hope you understand what I'm saying. So now you multiply your A sub 2, so the second result of your rotation, with this G sub 3, so your third Gibbons rotations, because now again the dimension matches, they match together. The J sub 3 is again a 3 by 3 matrix, so we can multiply it with A. And so if we do that, well, everything outside the submatrix didn't change. We have still a 5.39, 2.97, 3.9, 0, and 0. Okay, the element outside here, they didn't change. But inside the submatrix, you have now 2.27, 0, 1.06, and negative 0.82. Yes, okay. And yeah, this is now our upper triangle matrix R. And so now we know that if we apply all our given rotations to our original matrix, we get our upper triangle matrix R. And we also know that A is equal to QR and that Q transpose A is equal to R. Okay, remember, because Q is orthogonal, so its inverse is equal to its transpose. And so if you know that Q transpose A is equal to R and that G's that all those given rotations applied to A also give R, we know that Q transpose is equal to all those given rotations, okay? And so we know we can take the transpose of everything. So Q is equal to the transpose of the product of those given rotations. And you know that the transpose of something like A, B, okay, you know that the transpose of the product of two matrices is equal to, like here, A times B transpose is equal to B transpose A transpose. And it's the same thing for as many matrices that you multiply together. So if you here you get the result in the inverted order. Okay, you begin with one with the first rotation and you end with the third one, or if you begin from right and you go to left, you begin with the third one instead of the first one, and end with the first one instead of the third one. Okay, I hope you understand what I'm saying. It is just the rule for the transpose of matrix multiplication. Okay. So remember the geometric meaning of what we did. It's simply we rotated vectors. Okay, we have a vector first in 3 dimensions, and so generally what we did for the first column vector is we killed the y component. So here we have our vector in 3 dimensions. Here, sorry, this vector here, sorry. So first we will take it inside, rotate it in such a way that it now lies inside the zx plane. Okay, so the y component is 0. And then we will rotate it the second time such that the z component is also 0, so that it now lies on the x-axis. Okay, and for the second case, well, we project ourselves into this submatrix. But I mean, fundamentally, it's the same thing. Like here, we only want to kill the z component and not the y component, because we only want to kill this last element here. I mean, this element here, sorry, in this position. And so we begin directly here, but we directly project ourselves onto the x-y plane. Okay, instead of rotating onto the xz plane. Rotating, not projecting. Sorry. Yes. And that's it. So remember, this is simply, all we are doing is rotating. This is a rotation matrix. What you are doing. Why do we need those cosine and sine? Well, because if you multiply the identity matrix in how many dimensions you want with this matrix filled with cosine and sine, so negative sign, well, if you have, this identity matrix will rotate. Okay, like if you bring it in like that, we will rotate then like that. Or in the other way, maybe I don't remember, like that. This is simply rotate. Those are simply rotations, okay. And so if it works for the unit matrix, so if it works for the identity matrix, it can work for whatever matrix you want. And so that's all we are doing. Basically, we are killing the elements by simply rotating the vectors, such that the resulting vector has as a remaining component the norm of the old vector, and the other components are 0. Same thing if you are inside the submatrix. In this case, the column vector inside the submatrix will have at the end the norm of the old vector, and the other components will be 0. Okay, here also this 5.39 is, if I say no mistake, the norm of this this original vector here. We'll just check if it's true, but I think it should be true. 4.39 4 squared plus 3 squared plus 2 squared equals, take the square root. Yeah, it's 2. It's the norm. Yeah, well, I was just not sure, but yeah, it's 2. I mean, it should make sense because the vector is still the same. You are just rotating it, so the length fundamentally is still the same. It's just the coordinates that are changed. Yes. So yeah, I hope it was clear. So remember, the tricky part is just to calculate your cosine and your sine. Okay, cosine is top over hypotenuse, sine is the element you want to kill over the hypotenuse. The hypotenuse is simply the square root of this top element squared and the element you want to kill squared. Remember that the top element is also the top element inside the submatrix. Okay, so for the first case there is no submatrix because we consider the whole matrix, but for the second case here we go inside this submatrix, and so the top element is the first element of the first column vector inside this submatrix. Yes, and then you find your j and your I. Okay, so the position, those are the j is the column of the element you want to kill, and I is the row, and then you use your formula. So c I c j negative sine ij and sine ji. Remember, the negative sign is in the place of the element you want to kill. And then you apply your Gibbons notation, you consider your submatrix, very important. And then yeah, for the submatrix as usual, you put the Householder transformation to create the matrix. That is, you consider first your Gibbons notation inside the submatrix, and then you fill in the remaining diagonal with ones and everywhere as 0, so that the dimensions are again the same as your matrix A. Or for the Gibbons notation, you can simply just consider the place of the element you want to kill inside the submatrix, but to consider that inside the original matrix, like the element you want to kill inside the submatrix, where is it located inside the original matrix? And then you can find your j and your I accordingly, and you can just place it like that. And then again fill in the remaining diagonal with 0. Okay, if it would be a 4x4 matrix, you would still have a 1 here. You would also have a 1 here. 0, 0, 0, 0, 0, 0. Okay, if it was originally a 4x4 matrix, I'm just making that up now. And then, yeah, again, you get the same thing. It's just the same thing. Then again, at the end, you have your A is equal to QR, but you also know that if you apply all your Gibbons notation to A, you get R, so you can find your matrix Q, which is orthogonal. But we won't do that here. But yeah, you just need to do this computation here. This Q is equal to this to all your to the product of all your rotations transpose. That is your Q. Just do that multiplication and you get your result and you get your Q. And as I said, your R you also already got it once you did all your rotations. Yeah. So I hope it was clear, and I hope you could read it, and yes, thanks for watching.